right, part two here. Now, we're moving from one single transformations to combinations of transformations. Now, when we're doing that, remember the mapping method. The sequence does matter. The sequence is so important that if you mess up the sequence, you get a whole question wrong. Right? Now, so the key word will be follow the sequence and do not ever skip steps. Never. For example, you get dilation followed by reflection. Do not try to figure out what does the transformation do to my graph all together, combined together. Try to figure out what does each step do and get the end product step by step. So we start with x comma y. Then after a dilation of vector 2 from y, we know that from y change dx. Dilation of vector 2, that means time x by 2. So that becomes 2x. And y has not been touched yet. Now, followed by a reflection in y-axis. That means, again, reflect in y. That means change x. So I give x negative sign. That becomes negative 2x comma y. So this is what I mean by step by step and get the coordinate of the transformation. Right. Now, another example. If you know how to do this kind of question, pause here and try this one by yourself. All right. A dilation of vector 2 from x-axis followed by translations. Now, don't worry about translation yet. We do dilation first. So start with xy. We do a dilation of 2 from x. So 2 from x change y. We have x comma 2y. And we do translations next. So by translation of 2 units in the positive direction of x, that means x should be added by 2. Now, 3 units in the negative direction of y-axis, so that means my y-coordinate should decrease by 3 because it's negative direction. It's 2y minus 3. Now, some of you may ask why my coordinate is not 2 times y minus 3. Now, the answer is clear. If we go back to the definition of translations, when we're working with translation, we are changing the whole coordinate. We're not changing the variable. There's no such variable in coordinate. Remember, this x represents for a coordinate. This y represents for another coordinate. They just act like a constant. They represent for some sort of the number, right? So that means I just need to change the value of the coordinate. I change the value of the coordinate. So that means for some number y, no matter what format, when I translate, I just add a minus number on top of it. So that means mapping, change the coordinate. We're not working on the graph at all when we're working on mapping procedure. All right, does that make sense? Now, that's why your answer should not be 2 times y minus 3 altogether. This is wrong. This is wrong. All right. Now, next, use combination of transformations, and then we can determine the rules. So we worry about the graph in the end after we figured out what the transformation do to my coordinates. All right. Now, find the equation of the image of y equals to square root of x and the following transformations. Now let's do part A. So a dilation of vector 2 from x. So dilation from x means I change y. So that means y will be times by 2. Followed by reflection in x. Reflection x means change y, the negative 2y. All right. So we can build up the relation between x, y, and x dash, y dash. So this is the new coordinate, something we call x dash. This is new y coordinate, we call that y dash. Then we can write down the equation, x equals to x dash, and y dash equal to negative 2y, and y then equals to negative half y dash. Now this one actually comes from x dash, which equals to x. I just skip steps, right? Now, remember the ultimate goal for mapping is represent my original x, original y, with x dash and y dash. That's it. All right. Now, before we have the original graph in the form of y equals to square root of x, then I can replace x and y by x dash y dash. So y equals to negative a half y dash equals to square root of x dash. After some rearrangement, y dash equals to negative 2 square root of x dash. Now I can express the final answer. My equation after transformation should be this. Y equals to negative 2 square root of x. And that's the answer. All right. Now, if it does make sense, try part B yourself. Pause here and then check answers later. Now, part B. X comma y, same thing start with. Translation of 3 in negative direction of y-axis and 2 units in the positive direction of x-axis. X will be increased by 2, y will be decreased by 3. Now, after that, I will then dilate of a factor 2 from x-axis. So that means I'm going to time my y value by 2. Yeah, from x change y. Dilation means times. So I'm going to time my y coordinate by 2. Now, some of you may ask, oh, why this time I have this 2 outside the bracket? This is what I'm going to talk about and highlight in this lesson. Order matters. Order is so important in transformation. In this question, see that my dilation happens after we do all the transformations. This is the key. This is the key. My transformation will be done first, so the point will move. Then my dilation will adopt the effect from translation, then dilate the whole thing, dilate my graph after translation. Unlike before, unlike this example, I actually dilate first. After dilation, I can move the end product. So that's the difference between this example and this example. All right. Now, this means I'm going to dilate the whole y coordinate. Y coordinate is y minus 3 after translation. And dilation will make the value of the coordinate time by 2. So this is the value after dilation. Right. Now, we can have the following steps. X dash then equals to x plus 2. Y dash then equals to 2 times y minus 3 altogether. Then we can solve for x and y. X then equals to x dash minus 2. Y dash, a half y dash equals to y minus 3. Y then equals to a half. Y equals to a half y dash plus 3. All right, this is the expression of x and y in terms of x dash and y dash. That's it. Okay, now we have the original graph, y equals square root of x. We can then replace the original y, original x with x dash and y dash. We can rewrite that into a half y dash plus 3 equals to square root of x dash minus 2. Then we can rearrange the equation. Minus 3, y dash equals to 2 times x dash minus 2, and then we time everything by 2. Notice that here, we time everything by 2. So this is negative 6, negative 6. And we can write the end result. Y equals to 2 times x minus 2 minus 6. This is my solution. All right, that is the example of combination of transformation. All right. This is purely by mapping without considering the original graph, how the graph been transformed, not at all. Just looking for coordinate. That's it. Okay. Now, next part of this video will be how to determine transformations. This is another popular kind of question you may receive. Now, we've been doing quite a lot of questions that ask you to do, give you a whole lot of transformations, I'll give you a function and tell me what is the graph of the transformation. Now, another question will be, I give you one equation, I give you another equation of the transformation. Now you tell me what does the transformation bring my graph into that end product? That's this kind of question. Now, this method can be seen as a procedure of mapping, but reversed. Okay? Now, let's summarize, before we do that, let's summarize what we learned from mapping. And this is a table you might want to drop down in your own notebook. So mapping has the following conclusion. And let's go. Reflection in X would reverse my Y. Reflection in Y will reverse my X. You just put a little negative sign in front of the coordinate. Okay? It's the coordinate, not to the variable. Okay? Dilation of A from Y, change the X, times it by A. Dilation of B from X, change the Y, times that by B. Translation of H units in positive direction, K units in positive direction in X and Y axis will result in X value and Y value change, right? Translation is the easiest, but reflection and dilation, they actually sometimes they are actually sometimes confusing because in the prompt it's always X and Y, but to my coordinate it's actually the other variable that's not been mentioned being changed, right? Now let's have a look at one example and hopefully you get the idea. Right. Now, for example, I ask you to find a sequence of transformation that maps y equals to square root of x to y dash equals to -2 square root of x dash and work backwards through the following steps. You see how. Now, before we're looking for some sort of relationship between x dash y dash, x and x dash, y and y dash. Now, this idea still being the same. We're still looking for some sort of relationship between y dash and y, x dash and x. But this time we're working backwards. We're trying to get my end product, my end result, rearrange a little bit to make it looks very similar to my original graph. Make them look similar in the same format so that we can match everything. For example, now, if I want to match y with the y dash, that's okay. That's okay. It's okay at this stage to say y equals to y dash because they both are located on the left-hand side. But it's not reasonable to say x equals to x dash in this problem, isn't it? Now, if I say x equals to x dash, how about this -2? They're not equal. Guys, they're not equal. Because there's a 2 outside, if you say x equals to x dash, this right-hand side will not generate the same value as this right-hand side of the original graph, original function, right? So we have to make everything match. For example, something equals to something under square root. Something equals to something under square root. Only when they are in exactly the same format, we can say this square matches this square, this triangle matches this triangle. So this is what I mean by making them look exactly the same. So if I divide everything by 2 to my new graph, to my equation of the transformation, you see y dash, if I divide everything by -2, y dash equals to y dash over -2 equals to square root of x dash. Right, now we see the graph of the transformation is in the form of this. Something equals to square root of something else. And now we can match. We can say left-hand side equals to left-hand side. Right-hand side equals to right-hand side. Now we can conclude that x equals to x dash, y then equals to, no y dash, equals to y dash over -2. Right, remember, this is not useful. This is useless because you are expressing the original function, original variable with the variable of the transformation. This is not useful. This is useless when we're looking for transformation. Because transformation actually looking for, how can I express my coordinate of the function of the transformation, the new function? How can I determine the coordinate for new function in terms of the original function so that I can tell what manipulation, what operation, what number has been assigned to original variable so that I have the end result, if that makes sense. Now, let's say I rearrange to mix. Anyway, I'm talking about making the new variable the subject. Right, x dash equals to x, y dash equals to, I can time everything by negative 2y. Right, basically, this step, the whole step looking for, write the new variable in terms of the original variable so that I can do my observation. I can tell from this table, I say x dash has been transformed from x, and I have done nothing to it. I've done nothing to x, right? I don't have to do anything to change x into x dash. However, I have to do something to my y variable in order to make it into y dash. So before we have y, I have to do something to make it into negative 2y so that I have y dash. Does that make sense? So by some observation, I can say I dilate a factor of 2 from x-axis. Remember, from x, change the y, followed by a reflection in x-axis. So that means I reflect the in x, I change x, I reflect in x, I change the y, so that I can have two steps. Now, you can't have one step by saying dilation factor negative 2. It does not align with the definition. Okay, if we go back to the definition, dilation has to be with a positive constant of a positive constant of a. Right. Now, that means you have to split that into two steps, dilation, reflection. Now, by all means, you can say reflection first, then dilation. That doesn't make any differences in this question, in this particular question. But in some other examples, you may want to be careful. The steps, the order of the transformation will matter a lot. Will have great impact on your transformation. All right. Now, let's compare the differences. When you're looking for the image, which is the graph, which is the equation of the graph of the transformation, you are going to map xy to x dash y dash and find the expression of xy in terms of x dash y dash because the only information you're given is the original function. You don't have any information about the new function. You want to look for that. So that means you have to utilize the relationship between x and y, then change it in terms of x dash y dash, then find the equation. However, when you're looking for transformations, you're going to rewrite the graphs before and after transformation into the same format so you can compare and get the expression of x dash y dash in terms of x and y. Notice that this step is the most important step. They're so different. They're so different. Finding image, x and y being the subject. Finding transformation, x dash y dash being the subject. Now you can find transformation that maps x and y to x dash y dash by some observations. That's it. Now let's have a look at an example. Now this example asks you to do. Let's do it one by one. Example one. Find a sequence of transformation that takes y equals to x squared to the graph y equals to 2 lots of x minus 2 whole thing squared plus 3. Now let's go. We have the original graph and we have the new graph. Now I can't match terms, right? But the hint is by some observation, if I can manage to write something into something equals to something squared. Something equals to something squared. I can tell left-hand side equal, right-hand side equal. Right, so that means I don't need to change my original graph. I just need to change my new graph. That means, so this is relation between dash, x dash, and y dash. I can rearrange it. I can rearrange it by -3 to both sides. Divide both sides by 2. Now we move the whole graph into, whole equation into something equals to something squared. This is already the original graph. The original graph is already already in something equals to something squared. Right, we can then match them. So we conclude that y equals to y dash minus 3 over 2. And x equals to x dash minus 2. Does that make sense? Now, we can rearrange it to make x dash and y dash being the subject. So, I'm everything by 2. And y dash equals to 2y plus 3. At this time, x dash equals to x plus 2. Now, you can say, by some observation, I can determine the transformation as such. We can look at x and y separately. Now, I just want to change the x first because I think x is easy. I can translate. So this one actually tells me translation of 2 units in the positive direction. I'm gonna move it to the left of x-axis. All right, done for x. We now move to y. Notice that this time, to get my y into y dash, which is 2y plus 3, I have to, remember this, I have to time by 2 first, then plus 3. Does that make sense? If you plus 3 first, then time by 2. Now, if you plus by 3 first, then time by 2, you mess up the whole thing. You will never get 2y plus 3. So this order is so important that actually tells us you have to, let's do the green thing first. Let's do dilation first. A dilation of 2, of a factor of 2, from, now I want to change the y. That means my dilation should be from x-axis. Then what about the purple part? Plus. So that's translation of 3 units in the positive direction of y-axis. Now, notice that the only important thing is the translation must be done after dilation. Then, no matter when do you put this step, you put in as the first step, put in as the second step, put in as the third step, it doesn't matter. It doesn't matter because no matter how you change the x variable, the x coordinate, that will have no impact on my y. You can put it as the first step. You can put it as the second step. You can also put that as the third step. Doesn't matter. All right. This is the power of mapping. You can actually tell all the possibilities of transformation through mapping. All right. Now, if you get the idea, and you try part B yourself. Pause here, do it yourself, and see if you get the correct answer. All right, let's do part B. Now, originally, I get y equals to square root of x. Now we have y dash equals to square root of 5x minus 2. Now this time is actually easy. They are already in the same format because they are in the format of something equals to square root of something else. So we can match them. Y actually equals to y dash, x equals to 5x dash minus 2. And you can say y dash equals to y, and I need to make x dash the subject. So x plus 2 equals to 5x dash. X dash then equals to x plus 2 over 5. Now, notice that order matters. See, I did not need to do anything to my y, but for your x, the order is, now, you have to plus it by 2 first, then divide by 5. They are in 2 separate steps. Now, if you say, I just want to do dilation first. I don't want to make translation first. I just have this habit. I have this habit. Now what should I do? You can rewrite that into 1 over 5x plus 2 over 5. I did nothing but break down this division. Right? I divide everything by 5 separately. And this time you can say I actually do a dilation of 1/5 x. Then I do a translation of plus 2 over 5. That's fine. That's fine. That's 2 different methods. I'll write down the answer one by one. And you don't need to worry about this. Doesn't matter. Okay? So the first method, you do translation first. You can say translation of 2 units in the positive direction of x-axis. Then step 2, after that, you do a dilation of factor. Now notice that this time the dilation factor, you're not timing 5, you're dividing 5. Divide 5 means times 1/5. Does that make sense? Divide by 5 equals to, is equivalent to times by 1/5. This 1/5 is so important. From now, because I want to change x, I want to change x means I need to touch the y. I need to touch the y from y-axis. You need to dilate from y-axis in order to change the value of x variable. All right. Now, next, you can do, there's another way. This thing in black. You can say, I do a dilation of factor 1 over 5 because of this from y-axis. But when you do the translation, you gotta do it this way. You gotta do translation of, this time it's not 2 units anymore, it's 2/5 because of this. In the still positive because you move it up, you make the value greater, direction of x-axis. Both answers are fine. Both answers are fine. But you gotta watch out the order. You have to make them into the same order, sorry, not same order, into the correct order with the correct value for your transformation. All right. And this is the end of mapping method. In the next part of the video, I'll teach you how to determine transformations directly from the rule by some observations, but I do not recommend you to do it unless you completely master the method of mapping, because it's very risky and very easy to make mistakes when you determine transformations by observation straight away. Okay, thanks for watching. I'll see you in the next part. Bye bye.